that says DQ from the second FIFO, read the accumulator, add those two together, send that out into the world, and then also use it to overwrite the accumulator. Right. Any questions about these three stages? These are most of the implementation of the real version of this system, and we'll relate it to a spec shortly. Yes?
For the method consume, what kind of atonicity do you assume when manipulating the register?
Okay, so every rule runs atomically, and when you write to a register, you don't see that yourself if you read it again. All writes take place simultaneously at the end of one cycle, which is a natural interpretation of the way this will work when we lay it out in circuits. The register is just a box that things flow into, and we only see the results of what we write into it when we've finished a whole cycle. Yes?
So is there a static verification that you don't reuse a value in other variable in just rows?
Well, if you, the semantics are, if you write to a variable and then read, you get the old value. Because the read just gets translated into a wire coming from the register initial value box of your circuit. So it's all reasonable. But it can confuse people coming from a software perspective. Yes? Yes?
So I understand right, there is a concrete implementation where I don't understand as well. Are the queues themselves defined?
Oh yeah, I was going to bring those up next. They're not magic, they're just another library. Yes?
So you said if you write and then read, you get the old value, is that correct?
Yes.
So does this naturally lead you towards like a single static assignment type of style? Because like there's no way to change existing values in a given definition, for example?
That's probably accurate, which is, I feel like, roughly the same thing as saying functional programming style.
Yeah, sure.
All right, well, let's look at the queues that we're getting here. These are just coming out of a library and would probably be used over and over again. So, all right. I'm instantiating a library module called Simple FIFO, which is parameterized over the name the FIFO should have, the number of bits to use to represent the size of an array that's going to be allocated to represent the queue, and then the actual data type that gets stashed inside each of the cells of that array. I'll open this in a file. Let's see, so simple FIFO. You might not think it's so simple. It has 5 registers. ELT is a big vector. Read that as an array of whatever size we asked for when we instantiated the FIFO, where every cell has a value of whatever data type we asked for. But then there are 2 pointers into the queue, basically a head and a tail pointer, and they kind of will rotate around. If one of these gets pushed past the end of the array, it'll wrap around to the beginning again. So it's somewhat intricate. And there's an empty Boolean flag and a full Boolean flag that track the obvious conditions. And then we have the NQ and DQ methods, whose bodies appear up here. I'll page back to those. NQ, they should both fit on screen. So NQ, just an example of the kind of code that can appear in a method. We check whether we're full, and then we assert that we're not full. The meaning of an assert is the scheduler promises never to run any code that would hit a false assert. It's not like in, say, the C language where your system crashes if an assert is false. Instead, the compiler promises never to run code that could lead to a false assertion. So it's a scheduling or coordination mechanism. So we'll only proceed, a precondition of this code is that we're not full. Then we'll read the array and the head and tail pointers. We'll then read out of the array, we'll overwrite the array to take the NQ pointer and write the new data value into it. And then, well, now we've put something in there, so clearly it's not an empty queue anymore. We'll set false into the empty bit. Then we will increase the NQ pointer by 1, and this is modular addition, so it'll wrap back to 0 if necessary. And then we'll recompute the full bit in the appropriate way, and then we will actually take this next NQP and write it into the NQ register. And dually, in DQ, we check to see if we're empty, and we refuse to proceed if we're empty. And we read these same three pieces as above. Well, now that we're DQing, we couldn't possibly be full, because when this works, there'll be at least one available slot. We'll do a little arithmetic to adjust the DQ pointer as it's sort of chasing after the NQ pointer. We'll check whether they're equal, in which case we're now empty. And this is kind of interesting, why we save a register that records whether we're empty or full when there's actually an expression in terms of the NQ and DQ pointers that tells us what it is. One reason for that might be that the depth of the circuit that decides whether you're empty is considerably lower if you've cached that answer in a single bit that you can use directly, as opposed to recomputing and taking circuit depth that is roughly logarithmic in the size of your Q size. And then remember, the running time of a circuit is basically proportional to the longest path through inputs to output. And we'll get a longer path length if we have to repeatedly recompute this equality expression. So it can pay off to cache the result in a single bit if we assume on most cycles the value of the bit doesn't change, so we can just keep reusing it. And finally, we can return the dereferencing of the array to look at the position that the DQ pointer tells us about. Any questions about this implementation? Yeah.
Size, SZ,
Yep.
is 8-bit in your example? Or is it that
Yeah, I think that was an 8 over here. Size was 8 here.
Okay.
Interestingly, the proofs that we'll do will be independent of that detail. The spec doesn't even know that 8 number. It's just implementation detail. Any other questions here? So given the time, clearly I'm not going to jump into some proofs here. Let's see, we've about 4 minutes left. What's worth pointing out here? Well, with those FIFOs in place, I'm now doing some module composition to combine my 3 stages with the 2 FIFOs. And this is our implementation. And I think next time I'll start with going into the simpler spec that we'll prove this against, and then show how we actually carry out that proof, and then afterward generalize this pipeline reasoning to what appears in a processor, and we'll see how we can prove some processor optimization is correct. So last chance to ask questions here before we switch to lunch break. Any questions?
Plus in this case means what?
Module composition. It's an analog of the double pipe for parallel composition that we saw before. Though some of the details probably aren't the same as we're used to from software. Okay, that's it for me today then. Oh, there is an exercise in the DSSS 18 repository for today's content. You'll find it in the README for the Kami section after doing a Git submodule update.